Thanks. So last talk of the day. All right. So I'm very happy to be able to visit this happiest building on Earth, and that makes me feel happy as well. So I guess that's important. So I was initially trained in math, then I switched to do a PhD in psychology. Then I did a postdoc in the stat department. Now I'm teaching in a neuroscience department. So out of the different areas I got exposed to, math remained my favorite. So today I'm particularly glad I can come back to a math institute and give a talk. So it feels like home. So my lab is called the Brain Behavior and Computation Lab, or BBC Lab. If you search BBC Lab on the internet, you hit the first one. You can find us. Okay, but don't do it right now. So my lab is broadly interested in understanding how the statistical structure of the environment determines the kind of internal representation in the brain, and how this internal representation then in turn determines the behavior. And we are using a combination of theory-driven and data-driven approach to study this question. So in the lab, we construct theoretical models, we generate predictions. We also develop some new statistical data analysis tools to facilitate the test of these theoretical predictions. We have developed a bunch of methods. I have some names here. But for the sake of this talk, this is irrelevant because I'm just going to primarily focus on the behavior, given the theme of this workshop. In particular, I'm going to focus on the link between the prior knowledge we learn in the natural environment and the connection to the behavior output of the brain. So my talk will have two parts. The first part, I'm going to present a principled framework for understanding how the statistics of the environment influence perception. This is a framework we have been developing over the past 10 years or so. In the second part, I'm going to present some ongoing work on using image priors to improve the robustness of deep neural networks. All right, on to part one. So to address the theme of this workshop, in part one, I'm going to primarily focusing on an incredibly high-dimensional problem, which is a one-dimensional problem. It's higher than zero. A lot of people work on zero-dimensional problem. Okay, so and the reason is because I think in order to truly understand n-dimensional problem, we have to first have a solid understanding of one-dimensional problem. And furthermore, one-dimensional problems can be very tricky and difficult as well. Because for n-dimensional problems, we typically got to choose our favorite dimension. Then we just work on that. If that doesn't work out, we can choose a different one. Okay? But for one-dimensional problem, we have to fix it. Either you solve it or you leave it, right? Okay, with that, seems like there's no objection to that statement. Okay, great. So mostly one-dimensional, the last one will be n-dimensional, okay? So now, here's the fundamental question I would like to address. How does the perceptual system exploit the statistics of the environment to support behavior? And there have been two long-standing ideas in the field. The first one is called the efficient coding hypothesis, which was initially proposed by Howard Spallo about 60 years ago. The idea of efficient coding is the neural codes in the brain should adapt to the statistics of the environment to maximize information transmission. And in particular, the neurons in the brain should allocate more resources to the kind of stimuli that occur more frequently in the natural environment. And the second hypothesis, so-called Bayesian hypothesis, this one has an even longer history, which could at least be traced back to Helmholtz in the 19th century. So the idea here is the brain need to infer the property of the world by combining the prior knowledge here in the brain and the ongoing sensory evidence. So these two hypotheses or frameworks have been pretty influential over the past few decades or so. And the natural scenes, the statistics of low-dimensional stimulus variables have been well documented due to the research in the past few decades. Here I'm showing you one example. So this is a figure from a paper by Gershik-Laney and Simoncelli. So this is showing you the distribution of the orientation of local edges in natural scene. From this figure, you can see in natural scene, there are more cardinal orientations meaning vertical and horizontal, compared to the oblique orientation. Okay? And then the basic intuition is the natural scene statistics or prior distribution of this kind may bias the percept of human observers. And this intuition can be formalized mathematically into Bayesian observer models using Bayes rule. This is just the standard Bayes rule, which states the posterior is proportional to the product, the prior, and the likelihood function. Okay. And the classic work in the field emphasizes the perceptual biases due to attraction towards the prior belief. So here's one figure to illustrate the idea. So in this case, we have a stimulus variable theta, and we're assuming in this range the prior is monotonically decreasing. And then we assume the likelihood function is symmetric. Typically, we assume it's a Gaussian. Then when we multiply the prior and the likelihood function to obtain the posterior, we see there's a shift towards the peak of the prior, right? So this predict the perceived theta should be attracted towards the peak of the prior. Now we can use this framework to model the perception of orientation, right? In order to do that, we need to place the cardinal orientation on this side because the prior is higher, according to what we saw in the previous slide, right? I should place the oblique orientation on this side, right? So what this theoretical framework predict is human observers should exhibit a systematic orientation bias towards the cardinal orientation. That's the prediction of this particular model. This is remarkable because we just construct a model, right? It's easy, right? So this is the thing I typically tell my students who have never done any modeling work. So you should just try it. It's straightforward to construct a model and lead to very specific predictions, right? It's a very simple model. Then what will be the next step? We have a model, we have prediction, we want to test it against the experimental result, right? So how many of you think the prediction we just said is going to be supported by the experimental data? Okay. Who thinks it's not going to work? Why?
Then the talk will finish.
Okay, all right. So you have a great point. So that's sort of some next level stuff. Okay. All right. So this model makes a clear prediction. It seems pretty principled and elegant and simple, right? So when we actually go to look at the data, you're exactly right. There's a puzzle because the data shows exactly the opposite. Across multiple experiments, people found there is a systematic bias towards the oblique orientation. What that means is a slightly tilted bar will be perceived to be tilted even more rather than less. Then what do you do with this? We have almost like perfect model. It's very simple, it's elegant, lead to a prediction that's exactly the opposite of what people found in the experiments. Right? This is kind of, for a graduate student, this is one moment in life when field of science can be pretty hard. Right? Seems like you're getting everything right, but the last step, it's kind of the opposite, right? It's the worst case scenario.
So I missed something. Like, why did we believe the first model in the first place? I mean,
the first
the argument for that model. Like, why would you pick that cardinal bias?
The cardinal bias is because this. People think through evolution, we have learned prior of this kind.
So it's reasonable. It's reasonable sound.
Yeah. It is very reasonable, in fact. Yeah. So there are two possibilities. One is the model is wrong. The other is the data are wrong. I'm a pretty realistic person. I don't want to argue against the experimental data. So what I did is I sort of step back and rethink what might go wrong with this modeling framework. So what we have done so far is, we examine the natural scene statistics, and we say, okay, through learning, the system, the brain can learn a prior that sort of faithfully, represent that the environmental statistics. Then we say, okay, we have a likelihood function. That's another component in the model. I'm just going to assume it's a Gaussian because it's convenient, right? But then if you think deeper about it, this is actually a little bit arbitrary, right? This is a function. Likelihood function is a function depending on what kind of space you plot in it, it may be a Gaussian, maybe it's not, right? This is not a probability distribution. So essentially the problem, I think, is there is a lack of constraint here. We just made an arbitrary choice for mathematical convenience. That lead to a consequence, well, the consequence is that we generate prediction that's exactly the opposite of what people found. When I was a graduate student, I proposed a framework that combined this Bayesian inference with the efficient coding hypothesis, which was the other hypothesis we had on the first slide. So the nice thing about this framework is once you do that, now you realize both the prior and the likelihood function are constrained by the statistics of the environment. Through efficient coding, the kind of neuron, the property of the neurons in the brain or sensory representation will be determined by the statistics of the environment to maximize information transmission, right? And because the likelihood function is computed based on the response of these neurons, therefore the likelihood function is also determined by the statistics of the environment, right? So this is a very well constrained framework. It's determined by both. Let's now make the idea more concrete. Starting from this particular stimulus distribution, we assume, okay, through learning, in the stable environment, the observer can learn a prior that faithfully represent the stimulus distribution, denoted as P of theta. Then what about the likelihood? In order to get to the likelihood, I need to first define what I mean by efficient coding. So in this case, specifically, we propose the neurons should maximize the mutual information between the stimulus and their response subject to a resource constraint on the total feature information. So if you do a little bit of math on this, you solve this problem, you found in order to be efficient, the system, the square root of the feature information needs to be proportional to the stimulus distribution of the prior. And this makes intuitive sense because this is essentially saying the system needs to allocate the coding resource according to the stimulus distribution. Then how does this constrain the likelihood function? Well, we can use the following trick. Oh, actually, there's one more point I want to make here. If you're familiar with the Bayesian statistics, you may notice this is essentially the Jeffreys prior. Who knows Jeffreys prior here? Okay, great. Yeah, this also happened to be the non-informative prior in 1D. So there is a nice connection there. But the difference is in Bayesian statistics, we first start from a model. Then we find the prior that's non-informative. For the case of efficient coding, it's the opposite problem. We start from a prior, then we find a particular coding configuration that would maximize the information transmission. It's sort of the dual problem of that. Okay. Then how does the efficient coding constrain the likelihood function? All right, there's a simple trick we can do. We can first nonlinearly transform the stimulus scale into a different scale. We call it sensory space. And in this space, the feature information is uniform. Essentially, this function is the cumulative of the square root of the feature information, right? Essentially, we are warping the space. We're stretching it according to the square root of the feature information. In this space, because the symmetry is most parsimonious to assume the likelihood function is symmetric. Now, we can simply invert this mapping and plot the likelihood function in the original space. Now you realize there's something pretty interesting going on because in this space now, this likelihood function is asymmetric. And crucially, it has this heavy tail pointing away from the peak of the stimulus distribution. So this likelihood asymmetry is the key here because it leads to an effect we call it likelihood repulsion. This asymmetry would bias the Bayesian estimate away from the peak of the prior. Okay. Then on the other hand, this prior traction effect is still there, right? So it's like there were two effects. They were fighting with each other, right? The net bias of the Bayesian observer will be determined by a combination of these two. It's not a priori clear which one has a bigger influence, right? In order to figure that out, we did some math. In the end, what we found is very surprisingly and counterintuitively, this likelihood repulsion effect, generally speaking, dominates the prior traction. So we have a repulsive bias for the Bayesian optimal observer. And we can actually mathematically categorize that. We find the bias is a positive constant times the slope of the inverse of the prior squared. I want to pause and ask if there are any questions. Yeah.
So, what is the reason is better for the likelihood in the sensory space to be symmetric? So what is the...
Yeah, because in the sensory space, likelihood is everything is symmetric, right? The prior is uniform. The feature animation is also uniform. It's most parsimonious to assume it's symmetric there. Of course, if you assume it's asymmetric, there is some additional mechanism going on that can bias the system further depending on these specific assumptions you put in.
Okay, so by parsimonious just mean symmetry.
Yeah, symmetry.
Okay.
Yeah, that's right. Any other questions? Others? Yes.
Maybe an intuitive question, because when I think about predictive representations being kind of asymmetric, I have that intuitive idea that, because the future is that way, so it makes sense to be biased towards the direction of where I'm going to go, or the future. Is there an intuitive explanation of that?
Yeah, I think the intuition is the likelihood function is the stimulus, the statistics of the environment is encoded in those neurons, right? So the likelihood function already sort of took that into account. So it essentially undo, so this attraction due to the prior. It's already, in its calculation, it already knows, so the prior is gonna will cause the stimuli encode more that appear more frequently to be more accurate. It already take that into account. So, but in the end, it's pretty counterintuitive. Essentially, this is the kind of thing, when I was telling my PhD advisor, okay, in fact, this is the result we got. He was like, what the heck? Yeah, but we spent a few months confirming this is indeed the case. And yeah, this is kind of, I think, one case that math can be useful. Because, yeah, there's something that's slightly counterintuitive. We just can't quite just reason through it without relying on the math. Maybe in the future I will find a more intuitive explanation. But so far, I don't have one that's really, very intuitive. Yeah.
Is there some kind of center surround story or something? Or?
Not exactly. Maybe, I don't know. So I can think more about it. Yeah. Peter.
So this is all a story about human perceptual judgment.
Yeah, human perceptual judgment.
So have you, or can it be applied to other species, other
like a
organisms?
fish or something?
For instance, right, that would have very different distribution of...
Right. Yeah, I think there's some recent work done by Emily Cooper's group. I think they were measuring the natural scenes statistics for fish. I think they found the distribution look different, but they don't have the behavior. I don't think they measure the behavior. Yeah.
This might be silly, but could it be something as simple as gravity that would be different for fish? Because if something is like this, is likely to fall in our world or something. I don't know.
I mean, the cardinal thing. So that's essentially that's gravity as well, right? The reason there are more vertical orientations because of the gravity. But when we're on the ground, there's something to support that, right? Then you have the horizontal edges. But for fish, they're in the water. You don't need the ground to actually support that. Yeah, exactly. All right. So far so good. Sorry. Okay. Yeah, one more.
The point, and it may not be all that well formulated, but probably the psychological data is such that if you have a small deviation from a cardinal direction, right, we're able to detect that very quickly. Right? If you show a line that's just slightly off, I can tell. But if in order for me to tell that it's off like the 45 degrees, it needs to be quite a bit off. And for me to be able to see.
Yeah, I think that's kind of captured in the likelihood function here, right? The reason why you're saying if it's off a little bit, it's kind of easy to tell because the vertical orientation is well encoded because of efficient coding. So actually, there's one intuition for that. So because the prior is higher on this end, the encoding resource is also higher, right? The likelihood function should decay faster. Right? On the other side, we don't have much information. The likelihood is changing slowly. Right? In the extreme case, if you don't have any information, the likelihood function should be flat. right? If you have a lot of information, then you know it's definitely here and it's not here. So the likelihood would be very sharp. Yeah. I think that's a better intuition than what I provide on previous effect. Yeah.
Just wondering about reaction times in this data.
No. There's no reaction time here. All right, so yeah, basically we found the result. So this modeling framework can well account for the behavior in a variety of different orientation estimation tasks, including it can also explain when you change the noise of the stimulus, what happened to these biases. Essentially, it gets the basic patterns right in different experiments. So the second result I want to show is later we found this framework in fact predicts lawful relationship between the perceptual discrimination threshold and the biases. So the threshold and biases are two fundamental measures in psychophysics. They have been often studied separately. And previous work have generally considered them to be independent. But according to this particular framework, we predict the two, in fact, should be directly connected to each other. The idea, in fact, is very simple. We already know the bias can be written down as a functional of the prior or the stimulus distribution. Right? The discrimination threshold is essentially determined by the way how the coding resource is allocated. It's related to the inverse of the feature information. And through efficient coding, the feature information is proportional to the prior. Therefore, the threshold is also a functional of the prior. So both are directly determined by the prior. Therefore, the two are linked together. So this is elementary math, and you can just rearrange this. In the end, so this is what we found. The bias is proportional to the slope of the squared discrimination threshold. So here's one example. If this is a threshold curve and the bias curve would look like this, qualitatively, the zero crossings on this bias curve should correspond to the peaks and troughs of the threshold curve. And we went ahead, we test this prediction, and we found there's a large array of experimental results that support this. And we think this may be a new psychophysics law. And notice that there are a few existing psychophysics laws already in the literature, like Weber's law and Stevens' laws. But these are empirical laws that summarize based on the experimental data. And in this case, this relationship is derived based on this theoretical framework. So yeah, from a theory, sort of like a math point of view, this is kind of more satisfying, I guess, because you have a theory first, then you can test it in the experiment. All right, I would like to come back to this slide. And so far, I've shown you by combining this Bayesian inference and efficient coding, we're able to derive a more powerful framework that explains a lot of puzzling experimental findings that cannot be explained previously. But at the same time, there has always been this tension between this new modeling framework we propose and this classic Bayesian view. And in the classic Bayesian view, in fact, we can also do a little bit of math, and we can calculate the bias. What we found is, in this case, the bias should be proportional to the slope of the log of the prior. So we have been thinking, maybe there's a way to unify the two. Perhaps these are the two special cases of a more unifying theory. And more recently, we found we were indeed able to do that. This is reported in a recent paper we published a few months ago. So this is collaborative work with a fantastic collaborator, Michael Han, who was a former graduate student at Stanford. Now he has his own lab in Saarland University in Germany. So this is a COVID project. We just did it remotely. Actually, I'm yet to meet Michael in person. So and so essentially, what we did here is it's a very simple idea. We essentially relax the constraint between the encoding and the prior. We say, okay, we have a very general encoding model. There's a stimulus theta comes in, it's encoded through this nonlinear function f, it's one-dimensional. Then it's corrupted by some additive Gaussian noise. And then we got this merriman m. Right? This is a single equation describe this encoding model. Then we assume this merriman m is the signal that the brain used to decode this stimulus variable. Well, we assume the decoding is Bayesian. First compute the posterior, and then it try to minimize a LP loss function. Here we consider a family of loss function. When p equals 0, that's the map estimate. When p equals 2, that's the posterior mean, and so on. So this is a more general framework. But fortunately, we found we are still able to solve this analytically and just a few extra pages of math. Fortunately, then this is the result we found. We found that the bias in this more general framework consists of two terms. The first term is related to the slope of the log of the prior. We call this the prior traction. The second term is related to the slope of the inverse of the filtering information. We call this a likelihood repulsion because this term will lead to a repulsive bias away from the stimuli that's encoded better. Okay, that's the idea. So now let's consider some special case. When the encoding is homogeneous, J is a constant. So the second term becomes 0. So only prior traction occurs. This is essentially the regime of the classic Bayesian view. On the other hand, when the encoding precision varies very quickly, if this J term varies very quickly, then this repulsion will dominate. And this is what happened when we assume efficient coding. So this theory sort of nicely captured the two regimes that have been proposed previously. I'm just going to show you some example to provide a little bit more intuition. So this is case 1. We have uniform resources prior to the unimodel. In this case, there's only attraction, no repulsion. Okay. On the other hand, when the prior is uniform, the coding resources is heterogeneous. In this case, we only have repulsion. There's no attraction. Of course, we can have a mix of two. You can have both heterogeneous resource and heterogeneous prior. In this case, the bias is determined by a combination of these attraction and repulsion components. Yeah, essentially, these are just replots of the equations I had in the previous slide. Yes?
So, yeah, probably you explained it before when you described your 2024 paper. So what do you mean exactly by coding resources?
The square root of filtering information.
Okay, so
it's the total square root of filtering information.
Yeah, so maybe I mixed. So in one of the previous papers,
so what I mean is the simplest case. So if you assume there's only one neuron, okay? So the total square root of filtering information is essentially is the difference between the maximum firing rate and it's between the maximum firing rate and the minimal firing rate. This is your mean and this is your max. Right. So that was just a generalization to a case when you have n neurons. With one neuron, it's the dynamical range of that neuron.
But this is a target that you want to achieve in the sensory space?
Yeah.
Okay,
yeah.
so you have a target. You say, I want
right.
a sensory space like this, and I have this prior, so then...
Yeah, that's right. Yeah, that's right.
One more version of a related question. Like, there's probably some relationship. Typically, when you're doing this kind of psychophysics, there's some relationship to like receptive fields properties, right? Mm-hmm. And so I'm just curious, what's the interpretation here when you were mapped to receptor fields?
It's an interesting question. I never thought about it that way. We only have, this theory only have tuning curves. There's no, by receptive field, you mean the tuning curve. Yeah. So, one way to think about that is in this particular case, if the coding resource is higher, this range, that means the slope of these tuning curves are sharper here. Yeah.
So that's okay. So it's about the sharpness or the broadness of the tuning curve.
Yeah. So it's the rate of the change of the tuning curve. The slope matters. It's not about the magnitude.
Gotcha.
Of the firing rate. Yeah. Because filtering information is about the change of the firing rates over the stimulus space.
But then I guess the next logical question is sometimes the tuning curve has like a negative region. Like there's like there's some place that's like positive and some place that's repulsive.
That's receptive field, not tuning curve, right? So tuning curve.
Yeah, I guess tuning curve is just
negative. I don't know how to interpret that in terms of those filters, Because in the end, the filtering emission is computed based on the fan rate of the neurons, and not the receptor field property. Of course, the receptor field property gives rise to the tuning curves, but that's not exactly the quantity we use when doing these calculations. Yes. I think so. Yeah, you don't have a one-to-one like a mapping between the two. Can't really infer that. All right, I'm just going to all right, onto this slide. So when applying this to the data, we have also developed a statistical inference framework to reverse engineer the prior, the encoding resources and the loss function from the behavior report of the human observers. Essentially, we want to take the behavior data, then we can infer these model components. Now, suddenly, one realized that in doing so, we no longer have a one-dimensional problem. We have a problem with infinite dimension. Why is that? Because we are inferring these curves now, right? In principle, these curves they can be arbitrary, right? They're smooth. So we're studying a one-dimensional stimulus variable, but the nature of the problem can be high-dimensional, in fact, right? When your goal is to infer these curves, you can have many degree of freedom, right? But nonetheless, we have developed and validated a statistical inference procedure. We found it can reliably recover these components when you have enough data in your experiment. And we have applied this framework to a variety of different applications. If you're interested, you can check out our paper. And for the sake of time, I'm just going to present one example application to give you a flavor of what this look like. In this case, we're studying perceptual learning. The goal is to understand how the short-term stimulus statistics affect the perceived motion. So here's the task. So the data is collected in Package Lab about 10 years ago. The task is very simple. On every trial, the observer or the subject need to estimate and report the orientation of a set of dots. This task is relatively simple because the dots all moving in a coherent direction. It's 100% coherent. And the interesting manipulation they did is they manipulate the stimulus distribution for each subject, and for each subject, the direction of the dots is sampled from a bimodal distribution. And crucially, this distribution varies across the different subjects. For some subjects, the distribution is centered at the cardinal direction. For some subjects, it's centered at the oblique direction. And there are other subjects that are in between. So we have 3 groups of subjects. And we can apply our statistical inference framework to infer the encoding resource and the prior from the subject's behavior report. I'm showing you the recovered prior and the resources for the cardinal group. This is one of the 3 groups. You can see that the recovered prior is the solid line here. It reflects the experimental prior used in that particular experimental block. Right? We also explained the bias reasonably well. Now this is the intermediate group, the oblique group. So the interesting thing I want you to pay attention to is when we compare the recovered prior across these 3 different groups, we found that the subjective prior the observer used reflect the short-term stimulus statistics used in that block. It's not perfect, but their priors do adapt according to the experimental condition. Okay. Then on the other hand, when examining and comparing the recovery resources across the 3 different groups, somewhat surprising, we found they're relatively stable. We always got a high coding resource at the cardinal directions. Presumably, this reflects the natural science statistics of motion. There are more motion along the cardinal directions. And so overall, these results seem to suggest in an environment where the statistics of the stimuli is unstable, the encoding and the prior seem to be adapting at a different time scale. We think this is kind of an interesting possibility that need to be further investigated in future experiments. Any question about this? Short term, this is like, I think, a 1 hour of experiment, maybe 30 minutes. Yeah, it's about, I think, a couple hundred trials. Yeah, they can, they can kind of, I think they kind of, they get the basic shape, but they were not able to adapt that prior perfectly. Yeah, we were a little bit surprised the resource didn't appear to change at all. This potentially suggests the prior and the likelihood they are encoded maybe in different brain areas. Right? If they're encoded in the same group of neurons, presumably if the prior changes, then likelihood function should change as well. Any other question about anything so far? All right, if not, I'm just going to show my favorite slide here. We can indeed generalize this one-dimensional problem to n-dimensional problem. We can still solve it. If I was giving a talk in my department, which is the neuroscience department, I would probably never show this equation. But I figure this is a math institute. Maybe it is appropriate to actually show this. But the overall structure of the solution looks quite similar. So we can calculate the bias along each direction. Now we have an n-dimensional space, right? In order to describe the bias, which is a vector, we need to describe individual elements, right? It turns out still it has these two components. This is roughly speaking the prior traction is related to the log of the prior. And the second term is related to the noise covariance. This is like a repellent. So the challenging thing here is it's hard to test this. Doing the math is easy. The test this is hard. And why is that? Because this is a high-dimensional case. Right? In order to measure the biases and the noise for these high-dimensional variables, you need many, many trials to densely sample that space. Right? Probably few graduate students would like to run this kind of experiments. It's very tedious. So far, there haven't been much data set out there. If you know some data set which are potentially relevant to this, I'm happy to talk about it. So there's another one special sort of case that's simple and simple and interesting. When the noise is isotropic additive Gaussian, basically the encoding is uniform in that stimulus space, then the second term basically go away. And the first term also simplified into this. C is a positive constant times the gradient of the log of the prior. So in this case, we only have a prior traction. There's no repellent. And for those who are aficionados in machine learning, you may recognize this is essentially the score function. Right? And we're going to come back to this in a few slides. So the score function is essentially the bias of the Bayesian optimal observer. Okay? All right, now this is a great time to move on to part 2. I'm going to describe some ongoing work it's about using high-dimensional image priors to improve the robustness of deep networks. And this issue has been brought up multiple times in this workshop so far. And this is a more kind of an AI-oriented project. In order to claim you're studying AI, you have to study this. You have to study the prior of a high-dimensional stimuli, because few people in AI care about bars. Right? People may care about bar, but not bars. But we can study this. This is kind of just a fun project. I do want to sort of make a connection back to neuroscience, which is, we know deep networks is a very promising approach in studying the brain information processing, particularly in vision. So this is work pioneered by Dan and other colleagues. Deep networks are great. They're impressive in explaining the neuroactivity in many brain areas, in particular in visual cortex. You can do it in multiple ways. And I think this point has also been raised multiple times in this workshop. And these deep networks have a big problem. That's, they are, one of them is robustness. There are many more, but this is one of them. And this is our superstar panda. I think it had appeared at least 6 times in this workshop. So this is the 5th, and this is the 6th time. OK. So there are so-called adversarial examples. By now, I think all of you are familiar with this now. You can basically for a given image, in this case a panda, you can use some script or a mathematical procedure to find these small perturbations to that image. When you add to that, you get this image that are perceptually basically they're the same to us compared to the clean. They're the same as the original one, but when you put it through a network, it's, the network will be fooled. And okay, so this is old stuff. But now I would like to, I think this graph is new because I made it on my own. So what does this mean, like geometrically, right? So we have this image, roughly speaking, this 3,000, it's a 3,000 dimensional stimuli. It is a vector in a 3,000 dimensional space, right? Now you to close your eyes and imagine there's a 3,000 dimensional space, and there's a point in that space, which is this panda image. Then we can take a small neighborhood, L2 neighborhood, of that image, then we have this 3,000 dimensional ball in that space. So what adversarial example means is you have a 2,999 dimensional sort of plane that intercept with that small ball, right? If they intercept that, okay, these points are the adversarial examples, every single one of the dots here. If you can only imagine 3-dimensional, that's perfectly fine. So this is what adversarial example means and why they're interesting. Well, for me, first of all, it may lead to the discovery of more robust engineering solutions. Second, from a neuroscientist point of view, it may lead to new models or ideally better models of the brain. So I got interested in this problem during COVID. We were all at home. We got time to do some extra, to read a lot of papers. I realized that the adversarial robustness is a very big field, 1,000 papers or tens of thousands of papers. But fortunately, most of these methods don't work, okay? Maybe I should say unfortunately. So the one method people have talked about in this workshop is so-called adversarial training. This is kind of one method that works. And the idea is very simple. I think this one is also new because I drew this on my own. The idea of the adversarial training is essentially a form of data augmentation. Let's imagine a case if we can add every single point in this small L2 ball into our training set, right? Now that's going to, when you train the CNN, that's going to effectively push the decision boundary away from the area. So of course, practically, that's not feasible, right? Even though that ball is small, it's still a 3,000 dimensional ball. We can't possibly sample all the points. So what people propose instead is you can find the worst case scenario in this small ball. And these are the adversarial example. You can use a tagging procedure to find these, then you add them into your training set. It turns out if you add these, what that will also do is also going to push the decision boundary away. So this adversarial training works. But the problem with that is it won't generalize well to a different shape of this neighborhood. If you instead have a square, right, that's not going to do very well. If you have a ball, that's going to do well because it's trained based on that adversarial example. So I identified based on this ball, right? If you have an even more weird shape, it's going to, it's more likely it's going to fail. So this is adversarial training. I think we understand the intuition behind this one fairly well. And now I want to mention a second approach, and this one is more recent. This is called adversarial purification. Seems like this one also works. The idea, though, is very different from adversarial training. So for adversarial purification, what we do is we first purify the data using an image prior learned in some generative models. And here's one way to implement that. Starting from a noisy version of the image, we can use a denoiser. This is another network. We can first denoise the image to get a new image. Then we can put this through the classifier to obtain the image category. Now, I like this approach. I think this is interesting because roughly speaking, it is implementing a form of Bayesian inference. It's essentially finding the most probable image category condition on this noisy version of the image. If you do a few lines of math, you find, okay, this equals this equals this. And the first term is the probability of the image category condition on this. This is what's being computed in the CNN, right? Then we have this noise term, but here's the tricky thing. We have this third term, the probability distribution over images. This is like a nightmare, right? For many, many years, we have struggled to come out with good models of the prior over natural images. Well, we have prior over edges, but the orientation of the edges, but we don't have the prior over these 3,000 dimensional images, right? So there's a challenge. But fortunately, the recent progress in computer vision have provided us with some better and more powerful tools. And for example, here I'm going to focus on diffusion models. And diffusion models, probably most of you are familiar with this. You can basically sample images from these models, and these are models sampled, generated by the diffusion models. And because you can generate images like this kind, that means the diffusion models must encode image prior in some form, right? I hope that intuition is clear, right? So, and more recently, you can use this to generate videos. I mean, there is a video prior. It's not just on the images, right? So any of you are expert on diffusion models? OK, great. So I'm going to pretend I'm the expert. All right, I'm just going to give you 1 minute version on this. So what diffusion model does is learn to sample from this image prior. It has 2 steps or components. One is called the forward process. You basically add noise to this clean image, then you get these noise pattern, right? And importantly, there is also a reverse step for which you perform denoising. You gradually convert and remove the noise. In the end, you get this structured pattern. So what the diffusion model does is learn to denoise at every noise level by learning its score function. Geometrically, what that means is if you start with a random patch in this 3,000 dimensional image space, the algorithm follow this flow. Follow the arrows. The arrows defined by the score function plus some noise. If you just follow this, eventually you reach a point on the image manifold. So that's the image you generated. It's essentially a search problem in 3,000 dimensional space. And you are using the score function to guide your search. And notice that the score function is the bias in the optimal Bayesian observer, assuming additive Gaussian noise, which is essentially the kind of noise that's being added here. It's implicitly solving a Bayesian inference problem. OK. So, and the recent work have shown that the diffusion models indeed substantially improve adversarial robustness. What it did essentially, what I said previously, given an image, you can run the diffusion models, the forward step and reverse step, you get this purified image. Then you put this through a classifier. Okay. Importantly, attacking this system means you attack this entire thing, not just the classifier, right? You have to attack the entire system. We were able to replicate the result reported initially. This is work done by graduate student Yuezhang Liu in the lab, and we found that, in fact, so this forward step in the diffusion model is not important. You can just remove that. The results are similar, and practically depending on how you attack it, the number we got ranges from like 50% to 80% or so. But that's not really the point, because I don't do things in computer vision. I don't really care about exactly how big these numbers are. The question we are more interested in is how do the diffusion models improve robustness? Even though it's at 50%, that's already pretty good. It's not 0. Because for most of the models, they're exactly 0. For every image, you can find an adversarial attack. For CNN trained from the standard procedure is 0. So this is the case. We have about 40 to 70%. That's pretty good. It's a substantial improvement. So there's a little bit of hypothesis, so there's a little bit theory behind this, and people tend to think that the diffusion models increase robustness because it reduces the magnitude of the attack by shrinkage towards the clean image. So what that means is OK, got it. So what that means is if you do your adversarial tag, right, this is your clay image, you do your adversarial tag, and then you run your diffusion model. If your diffusion model push your image in the direction towards the clay image, right, that's going to effectively reduce the magnitude of that tag, turning a big tag into a small tag. That's going to increase the robustness of the system, right? That's the basic idea behind it. So it's kind of, it's doing Bayesian inference, implicitly doing Bayesian inference. And if the clay images are the prior modes, then you expect to see these attraction, right? And why are the clay images the prior modes? Well, that's just intuitive, right? You are using these clay images to train your model, and maybe they are going to become the modes the prior you learned. Yes?
One thing that we seem to have gotten away from is being similar to either brains or biological ways of this happening, or humans, because this is not necessarily something that brains do.
In this particular version, yes. Yeah. So because in this version, this is kind of like you have two versions of the visual system, right? You first do this, then you have this classifier. Yeah. In the way how people are implementing this right now, it's difficult to map this exactly onto what the brain is doing. Yeah. So and this is the hypothesis people have had in the so far in the literature, but curious enough, no one has really tested it. So we're interested to see if this is indeed the case. So we did some very simple numerical experiment. It's really straightforward. We just start from a clay image, then we do the serial perturbation. Then we ran this model through the image through the diffusion model. We get a purified version. Then we can quantify the distance of each of these images to the original clay image, and these are shown here in those numbers. Okay, and you can see after the purification, the distance to the original clay image. In this case, this is L2. You find these actually increases. This is not just a special example. This is another one, similar. So overall, the answer to this one is no. And in fact, after the purification, the distance to the clay images increased quite a bit. This is kind of puzzling, right? I mean, one interpretation of this is these clay images they're unlikely to be the prior modes, because if they are the prior modes, then because of these attraction effects, then you should see a reduction. But we don't really see that. There's a pretty profound increase. This is very, very bizarre. So geometrically, this is kind of what happens. This is your clay image. You perturb it, then you run through the diffusion model. Now you are all the way here. It's pushing them away. And that suggests this original hypothesis we have is incorrect. It's not like you are pushing this back towards the clay image.
What did it look like again? You had it on the other side. Can you just go back a slide?
Yes?
So that's what it looked like on the right then?
So these are the images. These images.
So it looks the same.
Yeah, they look the same, but the L2 distance actually this is not specific to L2. I mean, we use some other distance matter as well. It's pretty consistent. Yeah. So this is sort of one of the most like robust findings I've ever had. So regardless of how you do it, how you implement like a diffusion model, it turns out is always like this.
So when you are implementing the diffusion model, you're adding the noise, right? And then trying to recover.
Yeah, so there are two versions. Yeah, here, yeah, exactly. So that's a great point. I have two versions here. So for the blue curve, you're adding the noise, then you denoise, right? In the other version, I just run a denoiser directly. And in both versions, so and this is what I was saying earlier. No matter how you implement, there are different versions of doing. Of using the diffusion model. In the end, you see similar result. All right, let me just move on. Okay, this is the last few slides I have. I think we're good on time. So what we also found is, actually, these adversarial directions are not special. If you just pick a random perturbation to the clay image, then you run that through the diffusion model, that image will be pushed away from the clean sample as well. So essentially what happens is, after the diffusion model, this neighborhood got pushed into somewhere else in that image space. And this perhaps, if you think about the math, is not totally surprising because we can just do a Taylor expansion on the diffusion models around this point. If you do a Taylor expansion, you got x0 plus this fx0 minus x0. And then you have this Jacobian term and then times this perturbation, right? What this is showing is that this f of x0 is not equal to x of 0. So there is a systematic shift. You're pushing this entire thing away. And you also, and because of you have this Jacobian term, that's also going to, squeeze your image space along a certain direction and expand it along some other direction, all right? So
it's like not precisely encoding it in the first place or something. Like the neural network here doesn't precisely encode the thing.
Yeah, it does. Yeah, I mean, we don't exactly understand. Yeah, but I'm just presenting some curious, observation we have. Now, if you think about the consequence of this has a bad consequence because we are pushing these images away. The clean accuracy will drop because the classifier is trained based on the clean images, not these, right? Indeed, we found that clean accuracy dropped by about 10%. So this works against increasing adversarial robustness. Then why the adversarial robustness increase after all?
Question.
Yeah.
Would accuracy on a not seen out of distribution data be better actually, even though the accuracy here is not that good?
I don't think that is the case. Yeah, I don't think that is. It's possible. Theoretically speaking, it's possible. But
sometimes the neural networks are learning the noise first, and then they learn the actual features. So if you denoised it, I wonder whether, although it gets a little worse, but maybe it's better for generalization. I don't know.
Possible, but that's not what we found. Yeah, okay. Yeah, it's a good question. Okay, I think so this is the most important slide I have, and so we scratched our head quite a bit and for a few months because this is really puzzling. But in the end, we think we figured it out. This is very simple. We should have figured it out in day one. In fact, the reason is the diffusion model has a huge compression of the volume of that ball, and after we ran through this ball through the diffusion model, now the volume of that space got compressed. So if it got compressed so much, then there will be no decision boundary that intercepts with this transformed version of that neighborhood. And when we went ahead and measured this, so this can be done in multiple ways. We can do a PCA on these and PCA on these. As shown here, you can see with the original image, the spectrum is like this. But after the transformation now, for most of the eigen directions, the variance reduced quite a bit. We can also just directly compute the eigen spectrum of the Jacobian around x0. This is a little bit tedious. It takes about 2 hours to run this analysis on each image. So we were not able to run this on the entire data set. This is based on average about 100 images. We see that the eigen spectrum of the Jacobian for the most part is below 1, right? Which suggests there is a huge compression of the original volume. So why this can be helpful? The reason is because it reduces the gap between the clean accuracy and the adversarial accuracy, right? The clean accuracy, is based on classifying f of x0. Adversarial accuracy is based on classification of the worst case scenario in this ellipsoid. If the compression is so much, effectively f of m is identical to f of x0, so it's 1 point, then the clean accuracy should be identical to the adversarial accuracy, right? But that's the extreme case. Practically, we don't really see that. There's still a gap between the clean accuracy and the adversarial accuracy, but it has been much reduced. And we think this is the reason that caused the diffusion model to increase the adversarial robustness. So we also did this actual analysis. We found for the images that are not robust, after this transformation, the attack has a much bigger magnitude compared to the images that are robust. All right, so this is a summary and the diffusion models. bias in diffusion model cause two things simultaneously. One is the shift of the data that reduces the clean accuracy. This is bad. The second, at the same time, it leads to compression that reduces the gap between the clean and the adversarial accuracy. Is the second that's responsible for the increase. This is my summary, and this is my acknowledgement. I want to thank you for your attention. Happy to take. Not sure if there's time, but yeah. Okay.
What happens if you just run like some lossy, some lossy